Mm, I assume that everybody can see my screen.
Want to scroll through to just make sure you're able to. See that. Okay, so welcome all for joining us to the Matrix AI Spring Seminar Series. We also have students from the EC Research Seminar and several of the Matrix joining us today. We are kicking off our session with a phenomenal speaker of computer science at University of Maryland. She works on statistical and trustworthy machine learning, neural networks, deep learning theory, and specialization in domain adaptation, algorithmic robustness, and fairness. Furong is a recipient of the MIT Technology 5 Asia Pacific Award, the ML Conference Industry Impact Research Award, the NSF TRI Award, the Adobe Faculty Research Award, and the list goes on. And she is also the finalist for AI in Research, AI Researcher of the Year for Women in AI. She has received her PhD in Electrical and Computer Engineering in 2016, after which she spent 1 year as a postdoctoral researcher at Microsoft Research. All these topics that Furong is working on are some of the areas that Matrix is deeply interested in, and we are really honored to have her kick off the seminar season for us. So the floor is yours, Dr. Huang.
Thank you very much. Durisha, I think your voice is cut out periodically. I hope we don't have that problem when I speak. Welcome to the seminar, and thank you very much for inviting me to this wonderful event. So today I'm going to talk about trustworthy machine learning in complex environments. This will be, a summary of my recent 2 to 3 years work, and I'll cover quite a few topics in trustworthy machine learning. But I'll start by saying, we live in an era of information deluge. I guess even the smartest can find themselves overwhelmed by these highly dynamic and massive data streams they must keep up with to make informed decisions. So whether it's, our daily life of driving at a busy traffic junction, or the very high stake healthcare and medicine decisions that we have to make, or even in a very extreme case, say command and control in a modern multi-domain battle space. So there is an urgent need for us to develop machine learning models to augment intelligence for trustworthy decision-making in these complex environments. So for machine learning models to be trustworthy, they have to satisfy a few important properties. And in this talk, I'll focus on the three desirables here: robustness, efficiency, and ethics. So, however, there are some obstacles in our way to achieve each of these desirables. First, to obtain true intelligence with minimal human supervision, learning the complex environments as well as the agent's interaction with the environment is inevitable. And this setting is sometimes called reinforcement learning. Well, if trained from scratch, the agent has to use suboptimal policies to explore the environment, and this may take too long or even expose the agents to danger. And it's possible that you wait for several days just to train the agent. It still cannot stand up like a human. Even if we make it work now, later, if the environment changes and the agent receive an out of distribution observation, it will fail again. So reinforcement learning is very sample hungry. It's known to be very sample hungry, especially if we train an agent from scratch. But intuitively, we should not always learn from scratch. So let's say if we have spent a long time training a petrol robot with infrared sensors, should we learn a new policy from scratch? If we upgrade the sensor to be camera so that the agent's input space totally changes? And what if we like to use the robot in the nighttime later? right? It would be very convenient if the agent can quickly adapt to a total new environment or unseen input spaces, or even to a completely different task. Right, so especially in the very popular learning paradigm where you learn a strategy in a simulator, but deploy the learned agent in the real world environment. And the real world we live in, however, is unstable in nature. So distribution robustness is a challenge here. And this is called sim to real. Another challenge in interactive decision making is the robustness issue. As shown by many recent papers, neural networks are vulnerable to adversarial attacks. For example, we add a small but crafted perturbation to the panda image on the left, then a well-trained neural network classifier can misclassify it as a gibbon with a very high confidence. Although there are a lot of work studying and improving the robustness of these neural networks in supervised learning, the robustness of interactive decision making or reinforcement learning algorithms is not very well understood yet. But reinforcement learning is used in many high-stakes tasks. For example, autonomous driving, healthcare systems, understanding and improving the robustness of reinforcement learning agents are very crucial for us. So we must make sure that the agents behave robustly under these adversary inputs. Another important thing I want to mention in interactive decision making is the ethical development. So it's very unfortunate so far, ethical consideration is not necessarily the fast factor when you develop a model, right? So it's usually some kind of ad hoc approaches, if there is any approaches to consider ethical issues. But we do machine learning for human, right? Whenever there is human involved, we should always consider the ethical issues. So one thing that I specifically focus on is this fairness collapse under distribution shift during deployment. So the argument is that all these kind of high stakes decision makings concern our everyday life is not necessarily as we think of them as fair. They may have very different utility functions for different groups of people, especially if they've developed in one data set and really deploy it in another data set, then it is very likely that this unfairness is even more severe. So I'll probably talk a little bit about it today in my talk to address some of these issues. All right. So this is a very brief summarization of my group's recent progress addressing each of these challenges here. So apparently we had a lot of contributions in terms of understanding the robustness of decision making, as well as efficiency and ethics. Well, so focusing on robustness. So we'll probably be focusing on learning to adapt to distributional and adversarial robustness. So let's consider this situation. In most reinforcement learning algorithms, which is the prevalent way of dealing with sequential decision making, when the agent is in a new state or new environment, it basically learns everything from scratch, such as the petrol robot example we've seen before. But this is not how humans learn. So think about how humans learn. When we're in a new situation, we usually think of our previous experience and we wanted to find similarities, and we try to give a confident guess. Now that you've tried, for example, a strawberry donut and the mint cookie, as a human, you probably can make a very educated guess about how tasty the mint donut may be, right? So, but this is because humans learn by analogy. But can our agents also learn by analogy to speed up the decision making? Can a petrol robot use the knowledge collected during daytime using infrared sensors to transfer knowledge and speed up the learning of a daytime robot with maybe a camera, right? So we will use the idea of learn by analogy in different levels of learning and reinforcement learning. So first, when we're learning a single task, at some point, there are some unexplored states here. So of course, there are also some explored states, but most traditional methods would design a strategy to encourage the agent to visit the unexplored area. However, if we transfer knowledge from the explored area to like this unexplored area to infer what could happen in the remaining states, learning could be faster. And for example, if I am the state, I am the agent, I might think that there is also a flag in the upper right corner. So this is our main philosophy for learning to adapt, is to transfer knowledge from known to the unknown. Okay, so the main contribution here is that, kind of did some estimation of the model by utilizing some kind of internal structure of the underlying model that modeled this entire sequential decision process. And, we're able to reduce some computational and sample complexity. So the idea can be applied to learn multiple tasks as well. So where you can transfer knowledge from a learned task to unlearned task, even if they look very different. So we have a few projects related to this knowledge transfer, both in the single and multitask setting. Essentially, some of these works have improved sample complexity guarantees in the tabular RL setting. By tabular RL, I mean, the number of states and number of actions are finite and, usually small enough for us to deal with, okay? So, but today's topic, we're focusing on complex environments, right? So complex environments usually have very large state space. Also, in order to speed up learning in those complex environments, in recent work, knowledge transfer across tasks in the regime of deep reinforcement learning has been done and has been studied by the researchers. So here we observe that in reinforcement learning, actually, many of the tasks may share that similar transition dynamics because the system must all obey the basic law of physics. However, the observation spaces of these tasks may be completely different. Here is an example. So in a navigation environment, so as a maze environment, so the source task is observing this XY coordinate of this maze, and the goal, and of course, the target, the agent location itself, as well as the target location. But in the target task, what we do is essentially observe a top-down view of the entire maze. So it becomes a much larger state space, basically is an image, right? So the two observation spaces are drastically different, but the two tasks are structurally similar. So motivated by this question, right? So if we learn an optimal policy for petrol robot inverse sensors or GPS sensors, can we speed up the policy learning when the sensor of the petrol robot has been upgraded to cameras, for instance, and the field is still the room or the maze here, and the underlying dynamics, which have the basic laws of physics, are not changed. So rather than training an RL agent from scratch, our goal is to transfer knowledge from the source task to accelerate learning in the target task without knowing or learning any inter-task mapping. And this way we can learn even harder tasks from simpler tasks. So the solution is really to regulate the representation learning by learning and transferring a dynamics model. Let me explain it in more details. So in the source task, this is what we do. So we first encode the state observation, and then we pass the representation to the policy or value network. In our paper, as a first step, we kind of analyze this process and investigate what is a good representation. It turns out the answer is that it should be, compact enough but rich enough to approximate the values of a series of policy. And the details are in the paper, but intuitively, a representation map is sufficient for learning if we're able to find an optimal policy over the entire representation space, which of course require multiple iterations of policy evaluation, policy improvement. But learning such a good representation is not very easy because the observation space is usually very rich, like images or videos. So we propose to find a dynamics model, with the representation and to regulate the representation with the dynamics model. And the idea is based on this observation, we found that if you if you are able to make sure that your representation space give you a very good model prediction, then this representation space is essentially a better representation. Okay, so with that observation, then essentially in the target task, what we do is after we've learned this dynamics model, we're going to just load the dynamics model learned in the source task and kind of fix it and use it to regulate the learning in the target task. And this is theoretically guaranteed, because by transferring this dynamics model, we can guarantee that the dynamics model is transferable, and through this transferable dynamics model, we're able to learn the harder task in the target domain much faster. So essentially, the theorem also guarantees no negative transfer. Negative transfer means that you can transfer some wrong knowledge so that it finally hurts the target task, but this design can avoid such negative transfer. Okay, so we tested many different scenarios of observation changes. For example, in this half cheetah environment here, so we can have, the original observation space is a 17-dimensional vector space, right? So it's relatively simple because 17 is a relatively small number, but we can also just add some kind of artificial noise into the observation space to make it a much larger observation space, like 145 dimensional. And it turns out our method can just do the transfer pretty well from the 17 dimension to this 145 dimension. More drastically, you can see in the second scenario, when you are transferring from this 17 dimension to the actual image, which is a much larger, pixel observation, then we could also try to learn that task much faster compared to other baselines. So this is basically, we're kind of the first to study this transfer problem with such a big gap between observation spaces, and we're also, the first to achieve this vector to pixel transfer. Okay. So now, we've transferred knowledge to speed up learning to be robust to the distribution shifts and unseen inputs. But what about extreme form of perturbation that is adversarial? Let's go back to this adorable robot, of course, again, now that with knowledge transfer has a good knowledge of how the mint donut would taste, even though it has never tried one before, let's say. But here comes a mint donut. But there is a small bug on the mint donut, right? So in other words, a small perturbation to the input space. And it's like the bug is attacking the agent by perturbing its observation. Well, attacks like this could happen in many ways and could really result in bad some consequences we have motivated at the beginning of this talk. So really to avoid being attacked, we should be aware of our algorithm's vulnerability. So as the old saying goes, if you know yourself and your enemy, you will never lose a battle. So with the goal of learning to robustify, we first seek to know or to model the enemy and to, kind of study the different types of attacks. And then with the study of the enemies, we can robustify ourselves. We're going to evaluate and improve the robustness through some defenses. So let's start with attacks. I wanted to say that sequential decision making is extremely vulnerable, even more so than deep neural networks. So here is some results I wanted to show you. In the Atari game, some of you might have played Atari games before. It has image states, right? And it has discrete actions. And usually people use deep Q networks, to learn some agents to play against Atari, another agent or a human agent. So now here, the deep neural network, the deep Q network is the victim. So you can see in 4 different Atari games, when you add a very small number of perturbation, like the epsilon, to the state space, it's being very, very small compared to other, noises added to the neural network. So you can see a very strong attacker is able to bring the natural reward, to the lowest possible level. using very, very small perturbations. Essentially, to human eyes is even imperceptible. So this is very concerning. It basically means that these sequential decision-making systems powered by neural networks are really, really vulnerable. And it's even more vulnerable than just neural networks themselves. So we want to understand what is going on here, right? So that's how we wanted to study the pastime vulnerability. We call it evasion RL. So starting from a very well-trained model, the attacker basically tries to slightly perturb the input so that the agent output a bad result. And to understand the vulnerability of a trained agent, it's important to find the strongest attacker. So mainly there are two types of existing attacks for now for sequential decision making. And the first type is we call it heuristic-based methods. For example, they prevent the agent from selecting the best action in the current step in the myopic sense, right? So I only care about my current step, not in the future. In this figure, you can see the victim agent, which is this little cute robot here. The victim's original policy is to go right. So the heuristic attacker actually lead the agent to go up or go down. However, this kind of attack could be myopic, as I said, right? Because the strongest attacker, you can imagine, the strongest attacker can even lead the agent to the worst possible event of this trap here, right? But heuristic attacker may not have the ability to explore the environment and to understand that, there is a trap on the right and the plan for the future to lead it to first go to the right direction of going right, but then essentially go to the trap rather than go to the goal. So it can be shown that actually this myopic or heuristic-based methods are not necessarily exploiting the vulnerabilities of these RL agents. But it can be shown actually in a recent paper that optimal attack problems of identifying such optimal attack problems is actually an RL problem, a reinforcement learning problem. So naturally, the second type of attack is to directly learn a policy to generate the state perturbations. However, such RL problems is very, very intractable because in many environments, you have very large state spaces like images, and then these end-to-end RL methods are trying to learn a policy with both image inputs and image outputs, which is too expensive. And we usually cannot learn a good policy with a practical number of samples. So our goal here is really to achieve both optimality and efficiency, especially in complex environments. So we dive deeper into the essence of the evasion attacks in the RL problem. So the attacker actually perturbed the state, right? So perturb what the agent can observe. And the agent victim would select an action based on the perturbed state. Well, based on this observation, you can see this is equivalently as if we're just directly perturbing the victim's policy. Because if you perturb something in the observation space and the agent doesn't change its action or doesn't perturb its policy, then there's no harm, right? So you basically haven't done anything because the agent would do whatever they need to do to achieve their goal. So realizing that perturbing the state is equivalent to perturbing the policy, then the attacker's goal now is basically to minimize the policy value by designing some bounded perturbation in the state space, right? So, and of course, the goal is really to minimize the value here. So an end-to-end attacker would directly learn which state perturbation will lead to the lowest value. However, it can be a really RL problem, really, really large RL problem, as we said before. So we observed that only the second arrow here requires interaction with the environment. When you've had a policy, the policy is going to interact with the environment as if, how you derive that policy from the state is not related to the environment. So with that observation, we kind of decompose the problem into a much, smaller scale RL problem with a much smaller perturbation, of actions as the state, which is much more efficient to solve. And the other part of this is a non-RL problem, which just involves some kind of supervised learning. So this kind of decomposition really allows us to decouple the attack problem into a much smaller RL problem and a non-RL problem. And essentially, with theoretical guarantees, we can say that such a decouple guarantees that the strongest policy attacker is much easier to identify, and therefore the small RL problem is much easier to solve. Okay, of course, I'm not going into all these details, and this is supposed to be just a very simple kind of high level kind of description about what this work is about. And of course, compared with heuristic attacks, as we said before, that the heuristic attacks are not strong enough. They're very fast, but not strong enough. Our method actually compared with the heuristic attacks are much stronger and not less efficient, right? So now compared with the optimal but inefficient attacker, which is an end-to-end RL attacker, actually it's called SARL. This SARL is optimal, but our method is much more efficient as well as being optimal. So for very large observation space, such as image observations, our method is feasible wherever this SARL is not. Okay, so maybe we can see some results. So I'm actually already show you this vulnerability, but this vulnerability is really achieved by our result. You can see it actually significantly outperforms the state-of-the-art attack performance on a wide range of environments. So you can see on the Atari games here, I'm just showing Atari games. For other games or other environments, it's also in the paper. You can see the previous best attackers, which includes all these heuristic and strong attackers, right? So for these environments, they're getting worse results, but not the worst they can, right? Whereas you can see our attack basically achieved the worst possible, lowest possible rewards using very, very small echelons. So this is, in some sense good because, we've achieved the strongest attacker, but it's also bad news because basically says that, this AI-powered decision-making systems are really, really vulnerable. To give you an example here, so this is the Pong game, the Pong Atari game. So the victim agent is the right green paddle. And you can imagine, you see like the left one is the normal agent. It has a reward of 21, so it's doing pretty well. The red one, the green one. The green is our agent, and which is the agent being attacked. So you can see in the middle, this is the previous best attack. I won't tell you exactly which one this is, but I can guarantee that it gives a pretty bad reward compared to the natural reward the normal agent can achieve. But you can see the green one, it's still trying, right? It's not like completely failing. But if you look at the visualization of our attack, which is, we call it PAAD attack, the reward is actually going to the lowest possible reward. And you can see the agent is basically stuck there at the corner. All right, so now we've learned, like a model of strongest attack. It's time to study the defense, right? So how are we going to evaluate and improve, the robustness of RL algorithms through defenses? Okay, so there are many two ideas of robust training. To understand, we're going to train an agent that is robust during training. And the first one is similar to adversarial training in supervised learning to enforce the agent outputs like similar actions under state perturbation. And this is very intuitive, but it doesn't consider the properties of the sequential decision-making problems, and it doesn't consider the long-term reward, only consider the current step reward, which is myopic. Well, another method is, as we mentioned before, is to alternately train an agent and an attacker. And I consider the RL nature of this problem. So it can be really slow and optimal because you need to learn an extra attacker, and this attacker is trained through an RL algorithm, but it actually requires a lot of extra samples from the environment. It's actually doubling the requirement of samples So this is not efficient at all. It's very slow. So in our work, we kind of try to, find the best of the both worlds, right? So we propose a new method, which kind of directly estimate the worst case value without explicitly learning any attacker. And this can really directly optimize the policy based on the worst case value and the clean value together. So it doesn't require any extra samples. And kind of what we do is to propose a worst case Bellman operator. And this worst case Bellman operator, we can actually show that it's a construction operator, and its fixed point is the worst case Q value under the strongest attacker. So this is like a certification essentially, right? So a certified defense guaranteeing that you're always being cautious about the worst possible attacker out there. And the idea, is that in every future step, we kind of assume that the worst case action is kind of selected among all the actions in this adversarial set. And this adversarial set is the set of the action that agents may select under bounded state perturbation in the current state, and they can easily compute it by internal bound propagation methods out there for neural networks. If you're interested, take a look at the paper to find out the details. So as we, as we see here, this kind of Q, this kind of worst case Bellman operator Q can actually be learned through just the neural network Q network, which is not, terribly hard to learn. And a lot of existing works are, providing better ways to understand how to learn such a Q networks. Okay. So here are some empirical results. I wanted to say that this defense is actually really impressive. It has a lot of merits compared to existing state of the art. So first, it actually achieved state of the art robustness. By that, you can see that over a different variety of attacks with different strengths, like starting from a weaker heuristic attack to like the strongest attack you could imagine. This method, we call it Volcar PPO, actually got the best defenses, the best robustness compared to all the other baselines. So this is quite impressive. It's getting like state-of-the-art robustness. And not only that, if you look at the Pareto frontier between the natural reward and the robustness, you can see that this Volcar PPO also is the outermost compared to other methods, which means that it's not only getting the best robustness, but it's also making the least sacrifice in terms of the natural rewards. So that natural reward and the robustness trade-off. So in addition to that, what's even more impressive is that this method also achieved the state-of-the-art efficiency. As you can see here, that compared with other methods, you can use the shortest time to achieve the best robustness as well as the best trade-off between natural reward and robustness. So that's quite impressive here. I'm going to also show you some visualizations of the actual agents we've learned. You can see the first row here is the previous state of the art, which is a very strong defense method, which requires a long time to train because every step of training, they have to learn an attacker and learn how to be robust to that attacker. But unfortunately, if you look at this kind of walker agent is supposed to walk, it actually learned to jump with one leg for some reason that I don't know. But our suspicion, we suspect that is probably because this agent learned to overfit to a specific attacker. Because they have to learn a specific attacker during their training process. But if you look at the second row here, which is what our agent does as a defense, it basically, this walker learned to lower down his body, right? So, this is very making sense to us as humans because if we are under attack, it's very likely we would also lower down our body to walk. So I think this is a much intuitive general defense overall, which is interpretable to human being. Okay, so going forward, actually, I think I'm actually running pretty late, so I'm gonna skip this. This is a very interesting work of very recent work we did in terms of certifiable robust multi-agent decision making. The idea basically is, that we live in a world of partial information. So in order to make informed decisions, we kind of have to solicit information from all the other agents. So this communication can alleviate such partial observability, but it's also a double-edged sword just because, it can carry misinformation or adversarial attacks. So this work is basically trying to come up with a method to make sure that we're not hurt by such potential misinformation or adversarial attack by taking the wisdom of the cloud rather than overly trusting one of the agents. So that's the basic idea. We got a very impressive theoretical guarantees. I'm going to skip this and move on to the next topic, or just to wrap up this section. So you can see this section, we have done a lot of work in terms of, robustness to adaptation to the unseen input, or robustness in terms of the adversarial inputs. So after that, it's probably also important to think about what is, also required for trustworthy machine learning. I think the second thing that came to my mind is efficiency, right? So because even if you are able to do things in a very robust manner, efficiency is also quite important if you really want to make real-time decisions. So for this section of efficiency, I'm also going to very quickly go through some very recent work we're doing without giving too much detail, just to, get a sense of what other works that are going on in my group right now. So one things that we do is, we use tensor representation theory to extend some linear operations that is commonly used in neural networks to some multilinear operations. And this happens to have like theoretically justified reasons for us to learn much compact models and allowing us to take advantage of the spectrum control of these models to make sure that these models are not only compact, but also very, very powerful. And these can even be used in federated learning settings where, people are trying to learn from in a federated way, that all the clients participate into a large network and try to collaboratively learn a big neural network using their own data. So this basically is a work that we did in the 2020s and 2022. We have some nice results, can show that through such a tensorial neural network, you call it, right? So it actually have an improved generalization using the lens of compression. You can see that you can basically come up with some kind of generalization benefits for these neural networks. Okay, so another work is a theoretical understanding of model invariances of data augmentation. And the background for this is that a lot of the neural networks do not work very well when we don't do like data augmentation. By data augmentation, I mean, rather than directly fitting your raw data into a neural network, for these natural images, usually they do some kind of rotations, they do some kind of color jittering, or they do some kind of cropping and so on. So that's heuristic that we believe that these kind of transformations to the data do not really change the label, which is, whether this is a cat or this is a dog. So in that situation, people do this data augmentations, and I wanted to understand why these data augmentation are really helping us, and we kind of develop a theory to understand the models being more invariant to these data augmentations, and this will help with generalization. So it's a theoretical understanding of generalization benefits of model invariance by introducing some kind of sample cover induced by data transformations. Okay, so another thing that we did is to understand transformers, right? So this transformers is really important just because, it's achieving state of the art everywhere in all the applications, ranging from natural language processing, large language models. And nowadays also, they also have biology transformers. They have like, vision transformers and so on. But in the very recent work, we realized that these kind of multi-head self-attention modules in transformers are not the most efficient. And indeed, transformers have been criticized for them being very large size and really not environmental friendly. Well, so in a very recent work, as I'm showing here, we realized that we can even find a much more efficient variant of the existing multi-head self attention in transformers, and essentially can have provably guaranteed higher expressive power under the same size. So you could imagine you could drastically reduce the model size in this new architecture to make transformers much more efficient. And some results here, you can say for, like a video prediction result, we can see we're actually achieving the best, highest performance with the fewest parameters, which is quite impressive. Also for the image classification task on a, ResNet 32, which has 460K parameters, you can see using, for example, 10% of the original model, we kind of got like 91% accuracy as compared to the original 93% accuracy. I think it's pretty high still, right? But it's much more efficient. And we'll also do that on like graph neural networks when the the data is not just like images or languages. I also have some graph structure, and graphs are not easy to deal with. You cannot just simply sample from a graph, right? So we kind of developed a few kind of efficient models through kind of network model design. And for example, like, recent work on VQGNN, we kind of design a universal framework to scale up any neural networks, graph neural networks through some kind of vector quantization. So the idea is basically group them into different centroids and use code books to kind of essentially denoise the individual nodes. So essentially each individual nodes will contribute to a centroid, and the centroid would have a representative code book to represent the message passing for any of the nodes within that centroid. And also lately, we've been trying to develop a sublinear complexity training framework for graph neural networks using some kind of polynomial tensor sketch theory to sketch the nonlinear activations and kind of graph convolution matrices in graph neural networks to really speed things up. Okay, so I'm also gonna skip this federated learning work because I think we're running out of time. But I wanted to spend the last few minutes to talk about ethics. So I think ethics is a very important topic because machine learning should be in service of people, and machine learning should conform to social norms. So unfortunately, a lot of the existing research understanding, for example, how to make machine learning models fair is not considering a very practical challenge here, which is distribution shift. Imagine that, if you are in a hospital, right? So you train a models in a hospital, then this model will likely not only be deployed in your hospital, be deployed in another hospital, or your patients actually could change from time to time, right? The distribution of the patients in your hospital would definitely change over time. So in this case, there is a natural distribution shift. Even in financial industry, for example, right? You keep deploying these financial models for loan approval, for example, but these loan approvals will also face different clients over the time. So there is always a distribution shift, but existing work do not consider this distribution shift. As I said here, if you train a model in a hospital, it will not be fair in another hospital. If you've trained a financial loan approval in California, it will not be fair in New Jersey, or even in a very different state. So if you've trained kind of like some from celebrity data, it will not necessarily work for normal human, right? So based on that, we wanted to understand, how to make sure ethics even happen. How to make sure ethics is guaranteed even under such distribution shifts. So this is a recent work we did in terms of how to transfer fairness. So you can see that we have two domains share the same underlying data generation process. What I mean is like you have female and male from two classes, and you have two groups. The groups now is the race, like, is the sensitive attributes that want to make sure that, people from different race have the same outcome from these machine learning models. So we make some very mild assumptions, essentially some kind of intra-group expansion, which basically means that every group is self-connected with some certain transformation. What that means is like, I could do some kind of data transformation to transfer from my face to your face if we're both, let's say, Black female. Right? So that makes a lot of sense because there are some commonalities between their faces. And so based on this intra-group expansion and some kind of separation, we're able to show that, because accuracy in the source domain and invariances to such transformation would guarantee that you're accurate in the target domain. So in the sense that, if your source domain is some kind of celebrity data, and your target domain is some kind of normal people data, then this kind of, accurate, if you have an accurate model in the celebrity data, but make sure that the accurate model also is invariant to some kind of transformation, then it's going to be also be guaranteed to be accurate in the target data in the normal human faces. But, this still is not there yet, right? Because we want to make sure that it's also kind of fair, not only accurate. So then we kind of develop a theory, basically bound the unfairness within the worst group consistency, with the worst group consistency loss, so that, we see that as well as you're able to guarantee that the worst group consistency loss, which basically matches the invariances to the transformation, is guaranteed to be above some level, then, or below, sorry, the loss is going to be below some level, then you can make sure that you're not going to be very unfair. All right, so basically the idea is that if you are able to make sure that you have a fair, classifier in the source domain, and have the same ability of invariances across the domains, then you can guarantee that you're also fair in the target domain, even if there is a distribution shift between the source and the target. So basically the algorithm is just to minimize and balance the consistency loss across groups. Now, so we did some experiments, and you can see here, we did some kind of 3D shape data set, which is like a synthetic data set that we can simulate all kinds of distribution shifts just for the sake of understanding how does our method do under all kinds of distribution shifts. So this is a controlled experiment. And you can see for all different kinds of data shifts, like starting from subpopulation shift, as well as domain shift and hybrid shift, you can see our method is always achieving the best kind of fairness as well as accuracy under all kinds of distribution shifts we've investigated here. So I think that's a really impressive result. It's like the best of Pareto frontier for both the accuracy and unfairness. Okay, so now moving on to real world image data sets. So we kind of looked at like a UTK face and, and a fair face data set. So the task is to do gender classification, and the sensitive attribute is the race. As well, we do some kind of data transformation using kind of random augmentation. It turns out you can also see our method, which is like the red line, is achieving the best Pareto frontier in terms of accuracy and unfairness. So our method is really working very well in terms of both the synthetic data and the real world data. So now we also want to understand how does our method work other than on images, right? For example, in this tabular data where you have this new adult data set, which is, the source is the California label data set, but the target is some other state of the US. And the task is to do income prediction, and the sensitive attribute now is gender. We do some kind of a random perturbation, and you can see this is the result. On the left, you can see the accuracy versus unfairness. And on the right, you can see like the relative degree of unfairness versus the number of states. But apparently, you can see our method compared with the previous state of the art has a slight improvement, but not much. I think this is because we don't have a very good kind of powerful data transformation for the specific tabular data. In images, we know how to transfer the data, right? We know how to do like rotation, we know how to do cropping and so on. But for this tabular data, it's very hard to come up with a powerful transformation and yet make sure that we can pick out these invariances in the model. So that's the real challenge here for this tabular data. How do we make sure that we come up with powerful transformation so that we can make sure that the fairness is being transferred from different distributions? All right, so lastly, I wanted to say, this is the long-term vision. I wanted to say that, in terms of the long-term decision-making, it is also very challenging to make it fair, right, from the ethical perspective. For example, you can imagine like, a resource allocation or education process. When, people attend the STEMS program, a graduate program, starting from the day that they attend the program until that day of their graduation, there are a lot of decisions we have to make. There are a lot of decisions we have to make as educators, right? So we have to do resource allocation to figure out, when to give someone a fellowship, when to give them a TA-ship or a research assistantship and so on. So how to make sure that we make fair decision in terms of long-term rather than just the short-term is also a challenge here, and it's part of the research that is going on right now in my group. So finally, just wanted to conclude by saying that, we've done quite a lot of work in the recent 3 years in terms of robustness, efficiency, and ethics. And I've kind of covered, each of the most representative works in each of the 3 directions to you today. And I hope, this will give you a sense of what my group has been doing very recently. So this is the awesome group of students I work with. Without them, any of this work cannot be possible. So I feel very blessed to have a very strong group of students working with me every day. Also, I feel very grateful for the funding agencies that have been supporting our research. Without them, again, the research cannot be possible. And finally, this is the incomplete list of publications that are related to today's talk. So basically, I categorize them as robust ML, deep learning theory, model design, and scalable neural networks, as well as ethics in AI. Thanks. That's the end.
Thank you so much.
Thanks for having me.
Thank you so much, Furong. There is a lot of echo inside the room. Sorry, we have a new setup in the new building, so we are just trying to figure some logistics here. That was a phenomenal talk, and now I open the floor for questions. I see that Panos is eager to ask a question there.
You're on mute.
I'm on mute, sorry. Oh, now I'm on.
We don't hear you, Panos.
And that's the echo. Can you hear me now?
Yeah, I can hear.
All right. So, Furong, thank you very much for this amazing talk. All these are very interesting topics.
Thank you.
I had a first question about the tensors and how you use tensors for compression. I'm familiar with some exciting results that you present, but maybe you could also talk a little bit more about any guarantees that you were able to identify between compression and performance.
Yeah, that's a very good question. So, the kind of guarantee is on generalization. So it's on, generalization of neural networks. Basically the flavor of the generalization theory is just saying, the performance on the underlying distribution is going to be upper bounded the error is going to be upper bounded by some kind of empirical error on like this samples you observe, as well as the complexity of that hypothesis class. So basically, the idea here is that, you know, through this kind of compression using tensors on neural networks, you're able to drastically reduce the complexity of the hypothesis class, because you're guaranteeing, you know, the complexity is controlled by the rank of the tensors you use to approximate each layer. Yeah, so that's the basic gain here is, you know, as if you are, as long as you're able to train a decent neural network on the training data on this compressed neural network using tensors, then you're able to control the other term which contributes to the generalization error, right? So this term of empirical error is controlled to be very small. The other term is related to the complexity of the model. And if you control that complexity to be very small, then you have a generalization guarantee.
Got it. This makes sense.
Have another question from Connor.
Hi. Yeah, loved your talk. I guess I had a couple of questions that first off, can you hear me?
Yeah, I can.
Okay, perfect. I had a couple of questions, so I guess I'll just combine them into one. Regarding your first phase of the talk, about transferring knowledge using representation learning. How do you expect this to perform in more high-risk, real-time environments, such as autonomous driving, given large observation spaces, such as, you know, sensor fusion? And then I guess the second part of that question would be, how does your representation learning method compare to state-of-the-art model-based RL methods such as Dreamer?
Right, that's a very good question. So I first wanted to say that, you know, in autonomous driving, this very high risk tasks, I don't think RL is the only thing used there yet. And it's to me, to my knowledge, is basically a hookup of many different techniques, and essentially, you know, maybe ranging from supervised learning to control to reinforcement learning to imitation learning, and so on. Right, so basically what I was presenting here is more focused on the reinforcement learning part of things, but I could imagine this kind of representation learning, like the idea of transfer, can be used in many of these different approaches, but it will need adjustment or adaptation to such different tasks. So I think it has promising result. You know, it's very promising, but it needs adaptation to each of the components in such a complex system. Does that answer your question? I'm not done with the second one yet, but I want to make sure the first one is.
Yes, absolutely.
Okay, yeah, so the second question you're talking about compare with other state of the art. I wanted to say this is more focused on a transfer learning setting, right? So the basic idea of representation learning in, you know, the basic representation learning theory developed here is more for the transfer setting where you have some shared kind of latent dynamics. I think this is more, you know, if you're familiar with like the block MDP model, this is kind of like that, right? So it's like there is underlying block MDP model and you have the shared latent dynamics, which actually, you know, is quite true in a lot of settings. As we said, like the basic laws of physics is always going to be the same. We live on the same planet, right? So things are actually following the same transition dynamics. So, however, I feel like this method, when combined with the other state-of-the-art methods, could also be making things much more powerful. We didn't try that, but I have a strong belief in such a representation learning, and then transfer of this dynamics model could be useful, you know, in other more challenging tasks, or, you know, when you are trying to transfer between many different tasks. That's my take. I mean, that's my take, but yeah, I cannot guarantee things because I haven't tried them.
Perfect. Thank you so much.
Thank you.
Our next question is from Tej.
Hello, Dr. Huang. Thanks so much for the talk. I had a quick question about, so when you're talking about model adaptation from different data distributions, when you first train your model on your initial data distribution, and then you're, training it for the second data distribution to make that change, what is the ratio of the amount of data as well as the amount of training time required to make that shift over, or to make that shift successfully?
Right, right. So, are you talking about the first part, or or the ethics part? I mean, the first part.
Either of them. Does it change for either of them?
Right. So it's not a simple, how to say, so it's not a simple kind of, just retrain the model using the target data, right? So sometimes, for example, in the third part, that your target data is not labeled, so you cannot retrain it. It's basically like unlabeled target data and labeled source data, and somehow you're gonna train your model so that it works for target data. Does that make sense?
Right.
So it's not like you have both labeled source and target. And first gonna train the labeled source, then train the labeled target. It's not as simple as that.
Absolutely. I get that. I just wanted to know how much would you need an equal amount of target data to make the data distribution shift happen?
Oh, I see. Uh, so usually you have a lot of unlabeled data. Is what I'm. Oh, I see what you're saying. So you're basically saying that depending on different ratio of the source and the target data,
Yes.
how does the performance improve? So I would say that as long, so basically this is related to how your data is representative of the target data. For example, if you have a lot of target data, then basically you are able, it's not related to how much source data you have versus how much target data. It's more like whether your target data is representative of the underlying distribution.
I see. So
Yeah,
it
so
depends on how similar the two data sets are.
right,
Then it would
because you could imagine if I have very little sample from the target domain, I could have very biased understanding about what the target data is like, right? So I don't think the source and the target ratio is a problem here, but it's rather how much target data you have, whether it's a representative of the target distribution.
I see. Okay. And that would be representative of the training time as well.
Yes, yeah, definitely, because the training time is related to the number of data points you have.
Right. Okay. Thank you so much.
Sure.
And one question, Furong. In your first model, you talked about transfer knowledge, right? Like how you're transferring from one context to the other. And when you brought in the ethics discussion, right, with this, how well it transfers across different populations or different contexts or conditions, you kind of found the bounds of where, that discrepancy can happen, or what is the, or what are the bounds for it? But when you're transferring, don't you think there is, I mean, you found that there is a bound, but is there a way that the system that you're proposing, the dynamical system-based approach, that could address the challenge? Have you thought about it, like, to reduce that? Because this is something that we face constantly when we are using transfer learning models in the medical or healthcare applications. And I was wondering if you did any study on how well.
Can you see the screen?
Yes, I can.
Want to understand your question by bringing up the slide again. I feel like that's what you're asking here.
Yes, so this is more like trying to tie what you have done in your context one, which is like transfer, building these models that work very well for transferring the knowledge. And if you think of this case where you're thinking about ethics and how to transfer fairness, you said when we kind of transfer that knowledge, there is some underlying challenge where you have some kind of loss and which doesn't work fairly for everyone, right? The transfer might not work fairly for everyone. So my question was, is there any exploration in how the dynamic systems that you have designed, or maybe from other groups, in trying to reduce that barrier? Because this is something.
Yeah, that's exactly what this work is trying to do. Maybe I didn't make it very clear. So, basically, the idea we propose is to make sure that you do some kind of augmentation of the data. So what that means is if you are in an underrepresented group that you don't have a lot of data out there, then we were going to augment your data so that your data is richer. So the model can also pay attention to the data from this underrepresented group.
So that is, I think maybe I thought that you started this work in more looking at that loss boundaries. That's how I understood. But data augmentation to solve this problem seems to be getting a lot of heat, especially I'm thinking about the healthcare community, right? They seem to be pretty averse to doing that at this point because of a lot of challenges in how we are augmenting that data for some of the underrepresented
Exactly.
groups.
So yeah, I do have
are
a
we
recent
looking into
work.
this?
I do have a recent work in this NeurIPS 2022 that is on like autonomous learning of data augmentation. It works very well for images, for medical images as well.
Okay, so we'll look into that. Thank you.
Yeah, it's indeed not a very simple thing. Basically, is a balance between how you want your augmentation, how strong you want your augmentation, as well as you want to make sure that the augmentation don't go across the decision boundary, go to the other class. So yeah, indeed, you can find some kind of smarter ways through representation learning again to deal with such challenges. I don't have the slides here, but yeah, I'm happy to share that paper with you.
That'll be great. Thank you so much. I don't see any other questions. I know we are running a little late as well.
Yes,
But thank you so much for joining us today, and thanks to Panos for inviting you. So we hopefully will see you in person at some time here in San Antonio.
Oh, I really hope so. Thank you again.
Thank you very much, Furong.
Yeah,
Yeah,
thank you.
thank you.
Bye.
Bye. Take care.
Bye-bye.